Welcome, ladies and gentlemen, to an extraordinary journey through the fascinating realm of physics. Today, we delve into the captivating realm of special relativity, a theory that revolutionized our understanding of space, time, and the fundamental fabric of the universe. Imagine a world where time bends, where objects shrink, and the laws of physics defy our everyday intuitions. Special relativity, developed by the brilliant mind of Albert Einstein over a century ago, takes us on a mind-bending expedition into the depths of the cosmos. In this video, we unravel the mysteries of special relativity and explore its mind-expanding consequences. We'll embark on a thrilling voyage, journeying at speeds approaching that of light, as we uncover the profound insights that Einstein's theory has to offer. Prepare to have your preconceptions shattered as we confront bizarre phenomena like time dilation and length contraction, where the passage of time slows down and space itself morphs. We'll unravel the secrets of the famous equation E=2 and discover how it fundamentally connects matter and energy. Through engaging explanations and real-world examples, we'll witness the implications of special relativity in our modern world. From GPS satellites to particle accelerators, this theory underpins countless technologies and scientific breakthroughs. So, buckle up and prepare to challenge your perceptions of reality. As we journey through the wonders of special relativity, we'll marvel at the interconnectedness of space and time, unravel the mysteries of the universe, and gain a deep appreciation for the extraordinary achievements of human ingenuity. Get ready for a mind-expanding exploration of special relativity, where the ordinary becomes extraordinary, and the limits of our understanding are pushed to their very edges. Welcome to the awe-inspiring world of special relativity. Special relativity is a fundamental theory in physics that was developed by Albert Einstein in 1905. It revolutionized our understanding of space, time, and motion. Special relativity is based on two postulates: the principle of relativity and the constancy of the speed of light. Principle of relativity. The principle of relativity states that the laws of physics are the same in all inertial reference frames. An inertial reference frame is a frame of reference in which an object at rest remains at rest and an object in motion continues to move with a constant velocity in a straight line unless acted upon by an external force. Constancy of the speed of light. According to special relativity, the speed of light in a vacuum, denoted by c, is constant and independent of the motion of the source or the observer. This means that the speed of light is the same for all observers, regardless of the relative motion. Based on these postulates, special relativity introduces several important concepts and effects. Time dilation. Special relativity predicts that time is not absolute, but is instead relative to the observer's motion. When an object moves relative to an observer, time for that object appears to slow down from the perspective of the observer. This effect is known as time dilation. It means that moving clocks run slower compared to clocks at rest. Length contraction. Another consequence of special relativity is length contraction. When an object moves at relativistic speeds, close to the speed of light, its length appears to contract along the direction of motion as observed by an outside observer. This effect is also known as Lorentz contraction. Spacetime. Special relativity unifies space and time into a four-dimensional continuum called spacetime. In this framework, space and time are not separate entities but are interconnected. Spacetime is a mathematical construct where events are specified by their coordinates in 3 dimensions of space and 1 dimension of time. Relativistic mass and energy. Special relativity introduced the famous equation E=2, where E represents energy, M represents relativistic mass, and C is the speed of light. This equation demonstrates the equivalence of mass and energy, stating that mass can be converted into energy and vice versa. Relativity of simultaneity. Special relativity challenges the notion of simultaneous events. According to the theory, the concept of simultaneous events depends on the observer's frame of reference. Two events that appear simultaneous to one observer may not appear simultaneous to another observer in relative motion. Causality and light cones. Special relativity maintains the causal structure of the universe, where cause and effect relationships are preserved. Events cannot influence events outside their light cones, which are regions in spacetime that can be influenced by a given event. The concept of causality is crucial for maintaining a consistent and logical framework in relativistic physics. Special relativity has been extensively tested and has stood up to rigorous experimental scrutiny. It has far-reaching implications in many areas of physics, including particle physics, cosmology, and the understanding of high-speed phenomena. Its predictions have been confirmed by numerous experiments, and its mathematical framework forms the basis for more advanced theories like general relativity, which includes the effects of gravity. Special relativity is a theory that involves mathematical concepts and equations to describe the behavior of objects moving at high speeds. It introduces a new mathematical framework that accounts for the effects of motion on space and time. In this explanation, I'll cover the key mathematical concepts and equations of special relativity. Lorentz transformation. The Lorentz transformation is a mathematical tool used to relate the coordinates and times measured by observers in different inertial reference frames. It describes how measurements of space and time are transformed when transitioning from one frame to another moving at a relative velocity. The basic form of the Lorentz transformation for a single spatial dimension is x equals x vt t equals t vx/c2. Here, x and t represent the coordinates in one frame, x and t are the coordinates in the other frame, v is the relative velocity between the frames, c is the speed of light, and gamma is the Lorentz factor given by equals 1/sqrt 1 v2c2. The Lorentz transformation equations ensure that the speed of light remains constant in all frames of reference and account for phenomena like time dilation and length contraction. Time dilation. Time dilation refers to the phenomenon where time appears to slow down for an object moving relative to an observer. The time dilation factor, often denoted as t, is given by t equals t0 here. T0 represents the time interval measured in the rest frame of the moving object, and is the Lorentz factor. Time dilation implies that as an object approaches the speed of light, its internal clocks will appear to run slower when observed from a stationary reference frame. Length contraction. Length contraction, also known as Lorentz contraction, describes the phenomenon where the length of an object moving relative to an observer appears to shorten in the direction of motion. The contracted length, denoted as L, is related to the rest length L0 by L equals L0 again, represents the Lorentz factor. Length contraction implies that objects traveling at high speeds will appear shorter along the direction of motion when observed from a stationary frame. Relativistic velocity addition. Special relativity introduces a modified formula for adding velocities that takes into account the constancy of the speed of light. The relativistic velocity addition formula is given by v equals v plus u slash 1 plus v slash c2. Here, v and u represent the velocities of two objects relative to a frame of reference, and v is the resulting velocity of one object as observed from the other frame. The formula ensures that the speed of light is never exceeded, regardless of the relative velocities involved. Energy-momentum relation. Special relativity also relates energy and momentum of a particle moving at relativistic speeds. The relativistic energy-momentum relation is expressed by the equation E2 equals Pc 2 plus 2 here. E represents the total energy of the particle, P is its momentum, m is its rest mass, and c is the speed of light. This equation shows that the energy of a particle is not solely given by its rest mass, but also includes a contribution from its momentum. These mathematical concepts and equations form the foundation of special relativity and allow for the precise description and prediction of phenomena involving high-speed motion. They have been extensively tested and confirmed through experiments, providing a robust framework for understanding the behavior of objects in the relativistic regime. The origin of special relativity can be traced back to the late 19th and early 20th centuries when physicists were grappling with certain discrepancies and limitations in the existing theories of physics, particularly in the domain of electromagnetism. Electromagnetic theory. In the 19th century, James Clerk Maxwell formulated the theory of electromagnetism, which successfully described the behavior of electric and magnetic fields. Maxwell's equations predicted that electromagnetic waves, including light, propagate through space at a fixed speed. This speed was denoted as c and appeared to be independent of the motion of the source or the observer. Ether theory. To explain the propagation of light waves, physicists hypothesized the existence of an invisible medium called the luminiferous ether. According to this theory, light waves were thought to be vibrations or disturbances in the ether, similar to how sound waves are disturbances in air. The ether was assumed to be stationary and pervade all of space. Michelson-Morley experiment. In 1887, Albert A. Michelson and Edward W. Morley conducted an experiment to measure the motion of the Earth through the supposed ether. They used an interferometer, a device that splits light into two beams and recombines them to create interference patterns. The experiment was designed to detect the differences in the speed of light along different directions as the Earth moved through the ether. However, the experiment yielded unexpected results. No detectable differences were observed, regardless of the orientation of the interferometer or the Earth's motion around the Sun. Einstein's postulates, building upon the findings of the Michelson-Morley experiment and the principles of electromagnetism, Albert Einstein proposed a new theory of space, time, and motion in 1905, known as special relativity. Einstein formulated two postulates as the foundation of his theory: a principle of relativity. The laws of physics are the same in all inertial reference frames. This means that the outcome of any experiment should be independent of the observer's state of motion if they are moving at a constant velocity. The constancy of the speed of light. The speed of light in a vacuum, denoted as c, is constant and does not depend on the motion of the source or the observer. This postulate contradicted the prevalent belief in the existence of the luminiferous ether. Lorentz transformations. Einstein derived mathematical equations, known as Lorentz transformations, that related the coordinates and times measured by observers in different inertial reference frames. These transformations ensured that the speed of light remained constant in all frames of reference and accounted for phenomena like time dilation and length contraction. By combining these postulates in the mathematical framework of Lorentz transformations, Einstein developed a theory that fundamentally altered our understanding of space, time, and motion. Special relativity explained the behavior of light, resolved the discrepancies in the Michelson-Morley experiment, and provided a consistent framework for the laws of physics in the absence of the ether. It laid the groundwork for subsequent developments in physics, including the formulation of general relativity, quantum mechanics, and the theories of particle physics. Goodbye.